Space and Time, Einstein's Relativity. At the turn of the 20th century, physics, and with it the rest of science, was riven with an immense contradiction. But most of the scientific community simply shrugged it off. They believed that physics had solved the mysteries of the universe. They already had all the answers. And any discrepancies in experiments were simply due to measurement errors. Famously, Albert Einstein did not agree. In 1905, while working as an office clerk in Bern, Switzerland, Albert Einstein, still only 26, had published 4 scientific papers. That year became known as his Annus Mirabilis, or Miracle Year, because all the discoveries were game changers and all were worthy of Nobel Prize. In the end, Einstein won the 1921 prize for his description of the photoelectric effect, which helped to raise the veil over the structure of the atom. He also offered the first directly observable evidence of atoms through a phenomenon called Brownian motion. And thirdly, he linked mass, or M, with energy, or capital E, in his famous equation, capital E equals mc squared. The fourth paper concerned the, quote, c in this equation, which denotes the speed of light. And this mysterious speed was the cause of the great contradiction that came to define Einstein's work. His solution to it was the theory of relativity. The contradiction Einstein took on was a mismatch between the work of the two great physicists of previous generations. This was scientists at odds. The laws of motion of Isaac Newton and the laws of electromagnetism as defined by James Clerk Maxwell. Newton described nature in terms of matter moving like clockwork. Every motion of one object could be measured as relative to another. For example, cars moving side by side at the same speed, say 10 meters per second, are not moving relative to one another. Their relative speed is 0 meters per second. However, two cars moving toward each other at 10 meters per second have a relative speed of 20 meters per second. Maxwell's theories concerned a very different part of nature. That's Maxwell, not Einstein. And that very different part of nature was electric and magnetic fields. He explained that light was an oscillation through these fields, and his mathematics showed that the speed of light was always constant. This put the two great scientists at odds. Maxwell said light shining from the headlights of one car would always reach the approaching one at the constant speed of light. Newton's laws disagreed. They said that the relative speeds of the two cars would alter the measured speed of light beams. The problem was that no one was able to measure changes in the relative speed of light. Light was always moving at the same speed, even when its source in motion was toward or away from the observer. Einstein wanted to know why. At the age of 16, Einstein asked himself a question. What would I see if I was sitting on a beam of light? In the Newtonian context, Einstein would be traveling at the speed of light. Light coming from in front would reach his eyes at twice the speed of light. When looking back, Einstein would see nothing at all. Even though light from behind was traveling at the speed of light, it could never catch up. This was perhaps Einstein's first thought experiment, and he used more to flesh out what became the theory of relativity. One thought experiment sees a man, Bob, waiting for a train. Night falls, and a light on the platform is turned on. Bob measures the speed of the light beam as it moves along the platform. A train traveling at close to the speed of light passes by. Another observer, Bell, on the train measures the speed of the platform light. In a Newtonian universe, the beam should be steadily overtaking the train, but at a much slower relative speed compared to the platform. However, Bell gets the same value for the speed of light as Bob. Einstein had to question our most basic understanding of nature to explain why. Speed is a measure of distance against time. Therefore, light speed is a constant because time flows at different rates, and the dimensions of space shrink and expand. Objects traveling faster through space move slowly through time. Clocks on the station and on the train are not moving at the same rate. On the platform, Bob's watch is ticking away as normal, but he sees the clock on the train moving very slowly. Bell does not notice any slowing of time. The natural oscillations that we use to keep time, the swing of a pendulum, vibration of a quartz crystal, or energy fluctuations in an atom, are phenomena that obey universal laws. According to relativity, laws remain unchanged within the reference frame.